Okay. Right. I have already mentioned about a system which changes or alters the time variable. Well, we have some properties about the time variable and the changes in the time variable as well. What do we mean by that? For example, so these are the definitions. And from the definitions we will come up with some properties. The definitions that I will make are as follows. We define an even signal. You probably already know this. Is a signal for which x of t is equal to x of minus t. Alright? So if you flip around the origin, make a symmetric thing out of that, if the signal corresponds to the same function, then it means it's an even or a symmetric function. The odd function is another kind of symmetry. It's an odd symmetry, which says that x of t will be obtained from x of minus t by negating it again, minus x of minus t. Right? So these are the definitions of two time functions being even and odd. Now let's make an experiment. That's what I always do. I will ask you to try to prove mathematically, making a strict and rigorous mathematical proof of something very easy. And I urge you that you try to do it by yourself, and please try to do it. But you will see that things are very easy, and for some easy things you just presume that it's so obvious that it needs no proof. But that's not the point. I don't want you to make some very fancy mathematical scientific proofs or anything like the Fermat's theorem or anything like that. But I want to make sure that you understand what we mean by the term proof. Okay? That's something which most of the students lack. You should have a solid understanding about what a scientific proof means and how it is made. We have some misconception about proofs by examples, and that's usually because of the TV programs and some fancy people saying that this proves that, etc. Of course, it doesn't prove anything scientifically. In scientific or in mathematical terms, it's like proving the existence of an UFO, okay? Unidentified flying object. The name unidentified means that they are not proven yet. Okay? You cannot say that UFOs exist. You cannot say that they don't exist either. You cannot prove anything about that. You may believe or not, but that's not a proof. If you show me a UFO, look at that, that's a proof, it's not a proof, okay? So what is a proof? A proof has three folds in mathematics. You may choose either of these three paths. The first path is by construction. You start with the definitions. Okay, they are also called the axioms or the foundations. So you assume their existence and correctness. On top of that, you make your logical construction by mathematical means, of course. And you construct and you come up with the conclusion which I ask, and you say, you see, this is the proof. It's proof by construction. The alternative way, as I said, there are three ways. The alternative way is proof by contradiction. Contradiction is a very nice proof technique, and it is probably the most elaborated and used technique. It's as follows. I tell you to prove that something is something. The contradiction technique is as follows. You say that, let's assume the opposite. I ask you to prove that A is B. And you say that, let's assume A is not B. Start from that. Let's start from that. and you start constructing something, some formulations. You write this formula, that formula, you equate them, etc. You go on and you proceed with mathematical tools, and at some point you come up with a contradiction, and you see that it's impossible. What is impossible? It's impossible that A is not B. A is not B is impossible. So what does that mean? It means A is B. So that is the proof that you want to have. For example, I say that all the functions with a single variable has one dimension, and you say that, okay, let's assume that not all of them are with one dimension. Let's assume some of them are two dimensions, and then you come up with a contradiction. So that proves that, okay, all one argument functions are one dimension. That's a proof. So it's the second technique. The third technique, as we all know, is by induction. And induction is not giving many examples. It's not like saying that it works for 1, it works for 2, it's true for 3, it's true for 4, it's true for 5. So as you see, it's true for everything. That's not a technique, okay? It doesn't mean induction. Induction has only 2 steps. The initial step, for the first, you show that it works. For 1, it works. And then you do this argument. You say that for n, assume it's correct. If that's an assumption. Okay? You don't have to prove that it's correct for n. What you have to prove is it must be also correct for n plus 1, the next number. It's a link. If n is correct, you prove for n plus 1 it's also correct. Okay? Then that concludes the proof. It works for 1 and it works for n plus 1, given that n is correct. So these 3 things are the only mathematical proofs that I accept. So when I ask, or if I ask a question in the examination or anything, some question like, prove that the system has a pole at point blah blah, I would accept only these 3 methods. Don't come up with any garbage and say that I have proven it's a proof. It won't be a proof if it's neither of these. Okay, there are only 3 methods. By the way, this induction method, while I was explaining it, a nice example came into my mind, and that is the summation of integers. Summation, so let me open a parenthesis here. It's not an example of the course. It's an example for an induction proof. We know that summation I from 1 to n is equal to, that's something that they teach in the 6th or 7th year. Do you remember what this was? Yeah, n times n plus 1 over 2. It has a construction technique which is very famous with Gauss, Carl Gauss, when he was a very young student. He came up with this formula, and the formula that he came up with is by construction. He added from 1 to n, and then he added from n to 1, n down to 1, and added all of them. All the components gave you n plus 1, n plus 1, n plus 1, n plus 1, and there are n of them. So there is n times n plus 1 of all these things, but it contains twice of what you're looking for. So it's n times n plus 1 over 2. That is the construction, and I assume that you already know it. But I want to show you how you can prove it by induction as well. For example, what you need to know, say is this. Let's assume that, or let's see if it works for 1. From 1 to 1, there is a single element, and that is 1. And its summation is 1. Is it valid for, is this formula valid for capital N is equal to 1? It's 1 times 2 over 2. So it's 1 is a check. Now let's assume that for n, this is the formula. Then what is the formula? So that's the iteration that we need to show. For n, the formula is n times n plus 1 over 2. is it true that for n plus 1 the formula is valid? For n plus 1, what is the result? What must it be? It must be n plus 1, n plus 2 over 2, right? This must be the formula. Is it correct? The correctness must be checked like this. You take this, n times n plus 1 over 2, and you have one extra term, because all the summations up to there will be the same. There will be one extra term only, and you have to add n plus 1 to this. Okay? So, when you add n plus 1 to that, are these two the same? If you can mathematically show that this summation plus n plus 1 is equal to the case for n plus 1 times n plus 2 over 2 here, then that will conclude the proof. If you can show that these two are the same, then you prove the formula by induction. That's the way you do it. And I'm not going to do that, but of course clearly they are the same. Okay? So this is a nice example about making an induction proof, and that's what I would expect. Now let's come back to our original definitions. Sorry about that. These even and odd things. The question after this parentheses is as follows. I want you to show that this is an exercise. It's not a homework. It's nothing. You don't have to do it, but you have to do it. I mean, you should better do it. Okay? Show that every function has an even and an odd part. Now this is very, very important for the analysis that we will do in the future, like the Fourier analysis. Well, and what do we mean by that? Every function has an even and an odd part. It is telling me that every x of t, whatever it is, it may be periodic, it may be garbage, okay, whatever you can think of. But I promise that every function has or is composed of the summation of these two functions, xe of t plus xo of t. The first one is an even function, the second one is an odd function. You can decompose, split every signal into even and odd parts. Are you convinced with this? Can you see it? For example, if I give you a signal like this, okay, from 0 to 1, it's a box shape. It's neither even nor odd. It's nothing. But I'm telling you that it's a combination of the two. It has an even part and an odd part. By the way, the even part is this. This is x even of t, and the odd part, x odd of t, is this. This is minus 0.5 and this is 0.5. And if you add the two, you will get x of t. Okay. But this is valid for every function. So the question is, show that, prove that. Okay, so that is question number 1. Question number 2. Show that the multiplication of two even functions is an even function. This is easier, right? I mean, it's easier to see. But can you show it? Another one. The multiplication of two odd functions is even. What else? The multiplication of the even function and the odd function is odd. What else can we construct? We can say that if you have an odd function, its integral, symmetric integral from minus a to a, regardless of what that a may be, the odd function integrated will give you a 0. Quite simple. From minus a to a, the even function integration is equal to twice the same integral, this time from 0 to a, xe of t. This is again very simple, very trivial things that I'm writing. I'm writing these things to make sure that you have the skills. You make sure you have skills to prove something with these three methods, either of them. Okay, you should at least think about these. So, what else we have regarding the properties? So we already now started thinking about signals. We said something, some properties about the signal already, and that is the even and odd signals, the first items. What sort of other names can we think of? What sort of other properties we can give to the signals? And that is periodicity. What is a periodic signal and what is not a periodic signal? A periodic signal is a signal which has this kind of a property. If x of t is equal to x of t plus some certain capital T, this lowercase t is the free argument, the free variable, the time. That capital T is a certain number. If you can come up with this equation for a certain capital T, then you say that x of t is x of t is periodic with period capital T. This capital T will be the period now. Okay? Now this induces many things. For example, let me ask you this example question. Is this a periodic signal? This x of t. You switch on the function generator which starts producing a sinusoid. Assume that the thing that I'm trying to draw is a sinusoid. So is this a periodic signal now? Technically, I mean, that's the best you can do for generating periodic signals. You must start generating the periodic signals. But mathematically there is a problem. This is not mathematically a periodic signal because, as you see, it's not equal to x of t minus capital T. What is x of t minus capital T? Let's assume that capital T is properly selected. Then it will be something like this. And as you see, these two are not equal to each other. The first one starts at 0, the other one starts at minus t. So they are not the same. It means that a periodic signal can only be obtained for infinite extent signals. A periodic signal must start at minus infinity and extend to plus infinity. A sine or a cosine of t starts at t is equal to minus infinity and it ends at t is equal to plus infinity. It doesn't start from a point. Okay? So that's a mathematical thing that you have to be careful about. A periodic signal is infinite extent. It mustn't start or end at any particular point. Now in discrete time, the situation for periodicity is a little bit problematic. Now, please be careful about how I indicate a discrete time signal. You have already seen how I indicate a continuous time signal. It's x of t with parentheses, x parentheses t. It's the way that I notate continuous time signals. T is continuously varying. A discrete time signal is the array, or well, it's a memory sort of thing, discretely spaced. And we notate it like this: x square bracket n. Trust me, in the first exam, I will give you some continuous time signals and I will ask you to do something with it, develop a system or something like that, and you will give me a result in discrete time or a continuous time in notation. You will immediately forget what I told you, but don't do that. So if a signal is in continuous time, it's x parenthesis t. If it's in discrete time, it's x square bracket n. Okay? I don't want to see an x square bracket n for a continuous time signal. And you can say that, well, why is n not time here? I assume that n is time. Don't do that. N is the index, the integer. From minus infinity to infinity, like the numbers minus 1, 0, 1, 2, 3. Okay? So the discrete time is notated like this, and please always notate discrete times like this. And please always notate the continuous times like x of t. The periodicity of a discrete time signal is something a little bit problematic. Not as easy as the continuous time. It's like this. In discrete time, x of n must be equal to x of n plus m for m an integer, for some m an integer. For the other one, for the top one, this this capital T, it's just a real number. It doesn't need to be an integer number. Any real number will be okay for a period. The period of something can be pi. It can be 7 over 2. It can be 5 as well. But the period for a discrete time signal must be an integer. So this m must be 5, 6, 100, 1 million. But it must be an integer, not pi, not 0.1. Okay? So for an integer period, if you can find an integer period, you say that the discrete time signal is periodic. Now, I will give you 2 examples and I will ask you whether they are periodic or not first. And while determining whether they are periodic or not, you must also give me the answer. What is the period of these? So let's start with some examples. X of t, I will start with a continuous time example. Cosine 2 pi ft. Now I'm showing you some notation initially. These notations are critical for us. It's a cosine 2 pi ft. What is the frequency here? Time, t is represented by t, but there is also another argument in the function, that is f. That f is defined to be the frequency. And which is, by definition, the inverse of the period. And if you measure the period by seconds in time, it's very natural. The natural unit of measuring time is seconds for our system. Then the unit for frequency is 1 over seconds. 1 over t is 1 over seconds, which has a particular name you may remember or you may already know. What is 1 over seconds? Hertz. Right. Okay. So this frequency is hertz. For the rest of the course, unfortunately, we will continue with a different notation, which is the combination of hertz with 2 pi. So we will not say that the frequency is f, but we will say that the frequency is 2 pi f. And we will say that omega, a new term, it's not w by the way, it's the Greek letter omega, is 2 pi f. And since it is multiplied by a radian, the new term will have a unit of radians per second. It's not hertz anymore, it's 2 pi times hertz, that is radians per second it becomes. So whatever. So, we have already found the period. We found the frequency from this cosine, and the period is just the inverse of that frequency, 1 over t. From 1 over t, you will find that t is equal to 1 over f, of course, whatever that f may be. Let me give you or ask you some further questions. Suppose that we have x of t is equal to 3 times sine 20 pi t plus 4 times cosine 21 pi t. So this 20 pi t is also in parentheses. This is x of t. The question is twofold. Is this signal a periodic signal or not? And if you say yes, then what is the period? If no, of course, why? Now we are combining two periodical signals, and the period must be such a capital T that the whole signal, when you shift by an amount of that capital T, it will be exactly the same signal. So it seems to be a periodic signal. It is in fact a periodic signal. Okay, I'm telling you the answer. It is a periodic signal, but the period is not 1 over 20, and it's not 1 over 21. So what is it? If you go 1 over 20 seconds apart, this sine, the first one, will come to the same point in 1 over 20 seconds. In 1 over 21 seconds, which is a shorter period for the second one, the period of this one is a little bit shorter. The first one is 1 over 20, the other one is 1 over 21. It's a shorter thing. The second cosine will come to the same point, but they will be separated a little bit. So the period is neither 1 over 20 nor 1 over 21. What is the period? 420. Probably, yeah. It is way larger than that. And in the worst case, if you multiply the two, you will find the least common multiple. You have to find the least common multiple. Okay, that is the thing. The least common multiple of the periods. Is it really 420? Now, what is 420? 420 is a huge period. The first period was 1 over 20. The other one is 1 over 21. They are very small numbers. Probably they will meet at a sooner point. What is that sooner point? It is not 420. When will they match? What is the least common multiple of 1 over 20 and 1 over 21? I sincerely believe that the answer is 1. 1 over 20 and 1 over 21 will meet at 1. In 1 second, the first one will make 20 oscillations. In 1 second, the other one will have 21 oscillations, and then they will meet in 1 second. So the period of this x of t is 1 second actually. Right? That is something that we have to think about. What is the period of a sinusoid? Well, what are the common periods of when we combine different periodic things? What will we have? A more difficult question. X of t is equal to 5 sine 2 pi t plus 1 plus cosine square root of 2 pi t. confusing, isn't it? The first one has a frequency of 1, 2 pi times ft, so f is 1. By the way, I'm sorry about the previous question. It is 2 pi times frequency, so the first one is 1 over 10, the other one is 1 over 2 over 21. So you must find where they meet. It's not, it may or may not be 1 second. I'm sorry about the previous question example. But this second example is even more complicated than that. The first frequency is 1, the second frequency is, what is it? 2 over square root of 2. Which is square root of 2. And how about this plus 1 term here? What's going on? It's just a shift and it doesn't change the period, it doesn't change the frequency. Okay, it's just a phase. So don't worry about what I put as an additive term. But these two frequencies and periods, you must find a common period for these things, which is, as you see, way too complicated. But I'm telling you that these two are periodic. Okay? You will find the periods. It exists. It exists as long as both of them have some fractions or some numbers multiplying pi. But if one of them is multiplying pi and the other one is not multiplying pi, then it will become an irrational number. And if two numbers are not rational among each other, then you will never come up with a common multiple. The common multiple will be infinity. Then it will be not a periodic signal. But these two are, by the way, periodic signals. Both sinusoids have the term pi that is multiplying t. If one of them has and the other one doesn't have, that would be a problem. Okay. Now comes an even more confusing discrete time, this time signal. It's this. Let's start with the easier discrete time. Cosine 2 pi over 8 n. X of n is equal to cosine 2 pi over 8 n. What is the period here? The period here is deliberately given to be very easy. It is 8. 2 pi times frequency times n. But that frequency is 1 over period. So what is that frequency? It is 1 over 8. Therefore, what is the period? 8. Another example, x of n is equal to cosine pi over 5 n. It's 10. Okay. Another one. Seven pi over 8 n. Hmm? 16. The period is 16. It happens, or it looks like the period is 16 over 7, but 16 over 7 is not an integer thing. You cannot go 16 over 7 units. The first integer that comes as a multiple, an integer multiple of that, 16 over 7, is 16 itself. Therefore, the period here is 16. X of n is equal to cosine n. Hmm? 0. Period is 0. What do you mean? Well, the period looks like 2 pi, yeah? Okay. So what is the integer, or what is the multiple of that number that becomes an integer? 2 pi is not an integer number. It's like 16 over 7. 16 over 7 can be multiplied by 7. and then you will have 16. So it's 2 pi. Multiply it by something to get an integer. What is that integer? No. You have to multiply by an integer. Some multiple amounts of this period. The period looks like 2 pi, right? If the period is 2 pi, I want to multiply, since it's not integer, I want to multiply it by some integer numbers to get an integer. Yeah, well, 10 to the infinity. Well, it's infinity. Since pi is an integer, an irrational number, you will never make it an integer by multiplying with an integer. Because it's not ratio of something. It's irrational, no ratio. Which means that cosine n is not a periodic signal. And similarly, so let's put a cross here. It's not periodic. Similarly, x of n is equal to cosine 100n is not periodic either. Okay. Or x of n is equal to cosine n over 1000. These are not periodic. So inside a sinusoid, you should better have a 2 pi term so that the discrete time signal could be considered as a periodic signal. Otherwise, it will not be a periodic signal, at least technically. All right. Now, before giving an end, the last types of signals that we will be familiar with. We will continue with all these things. I mean, we will come back to these things. I'm making some sort of an introduction to the general concepts. I'm giving you glimpses of what we will be covering and all that. The next thing, so what have we seen? We have seen even and odd signals. We have seen periodic signals in continuous time and in discrete time. We have seen scaling and shifting in time. Okay, x of t minus 3 over 2 sort of things. So you should be prepared to such things. The next thing is an important signal called the unit step function. Some functions or some signals are so important that they have their names and they have their notations with that. This unit step is one of them, and the notation for that is the function that we have is called u of t. That u comes from the unit step, and that unit step function is a function corresponding to turning on something, switching on. It comes to be 0 up to time is equal to 0, and at t is equal to 0, it immediately becomes 1. So this is u of t, and then goes to infinity. You turn it on. This is called the unit step function, and step name is quite obvious, I guess, from the shape, as you see. Such important signals can be used, some very basic and important signals can be used to construct other signals. For example, can you describe this signal from minus 1 to 1, and the value is, let's say the value is not 1 but 2, x of t. Can you represent this x of t in terms of u of t? That will be critical because you will know how to deal with u of t, and whatever happens to that u of t, it will indirectly affect this x of t. So let's try to write this x of t in terms of u of t. Can we do that? I guess we can. What is the starting point? I mean, any candidates about? It is twice of u of, I'm asking you in terms of u of t, not a single u of t, of course, multiple of u's. 2 of u of t minus 1 or plus 1? Okay, it is a +1 if you are trying to shift the u to the left. If you are moving your signal towards left, you must add some positive value to the time. That's the only way to go left. Because as you see, it becomes t plus 1, and it makes at t is equal to -1, it becomes 0, and that is the point of u of 0, which is like this, okay, this jump, the step. Okay, u of t plus 1. But that's not this box, of course. Yeah, we must subtract an extra residual u of t that starts from the point of 1 to u of, this time -1, because that's the shifted thing. So the situation is as follows. You have this thing, and from that you subtract this red thing. And the residual, it doesn't look very red, sorry about that. The difference between the black and the red signals is this thing that is left in between. Okay. So u of t is such a basic signal. And if your signal starts at some point, or at t is equal to 0, for example, we usually notate it like this. We say, do you remember my periodicity question? I said it was all zeros and then a sinusoid like this, x of t. And I asked whether this is periodic or not, and it's not. So x of t is probably sine 2 pi ft, whose f I don't know, times u of t. So by multiplying with u of t, I force it to start at t is equal to 0 point and go onwards. So it's not periodic because it's not sine 2 pi ft, it's sine 2 pi ft times u of t. Anything multiplied by u of t will be spoiled. It won't be periodic anymore. So u of t is some important signal. We can stop at this point. We have other important signal types. We will continue tomorrow.